So our next speaker is Dan Andrews, and Dan is the mission manager for Viper. Previously, he was the mission manager for the LCROSS mission that we're all very familiar with, and he is going to be giving a status on Viper. So Dan, please take it away.
So it's a pleasure to be here talking about the Viper mission and giving a mission update. I also want to acknowledge LRO as well. It's a full circle for me. When we led the LCROSS mission, we were, of course, a co-manifest with LRO all those years ago. And now we're kind of coming full loop and back to the moon again and doing more detailed investigations of what both LCROSS and LRO had discovered and continue together. So Viper, which is Volatile's Investigating Polar Exploration Rover, is part of the overall Artemis plan to return humans to the moon and to enable them to stay. Of course, you don't need Viper to be able to get humans successfully to the moon, but you may need what Viper has to learn about in situ resources in order to be able to support humans for the long term. Viper mission parameters, we're nominally about a 100 Earth Day mission, but that's going to be a function, of course, of the actual traverse and site selection that we make. You're going to be hearing a lot more about that from Cola Creek coming up right after my presentation here. We're carrying 3 different instruments, but really 4 instruments. 3 of them are spectrometers, a neutron, near infrared, and mass spectrometer. And then we have a 1-meter drill that we're getting commercially that, of course, is going to be able to bring up materials from below in order for us to understand both the horizontal and vertical distribution of water and other volatiles. Number of subsurface assays or drill sites that we plan to have. We think we need about 18 in order to be able to get the right statistical makeup in order to make our determinations about the different ice stability regions that, again, you'll be hearing more about coming up. But we think we'll be able to do many more drill sites than that, which will only make our data more robust. The key driving energy cases for our design have to do with dark survivability and the permanently shadowed region working duration, meaning with drill, all the instruments, locomotion, getting in and then getting out of the PSR. And so those 2 parameters, as you can see there, nominally 70 hours at this time, 12 hours. Those are key driving design capabilities. And as we're about to approach our CDR in the fall, these will get locked in, the correct values will get locked in, and then, of course, we will optimize the mission traverse around those parameters. Our distance traveled, which is not a requirement, but we do have a goal of around 20 kilometers. We might do more or less than that. Again, a function of the traverse. And then the traverse will be baselined along, of course, with the site selection at CDR. Super quick tour of the surface segment, which is our name for the rover with the instruments. You can see the blue text is showing those instruments that I made a really quick reference to along the bottom. Downward facing to the soil are the M-Solo instrument, which is a mass spectrometer, and then our near-infrared spectrometer, NERVIS, are both down there looking at the surface underneath the rover and any of the tailings that come up from the drill. You can see the top part of the drill poking out the top of the rover. And then our divining rod, if you will, is the neutron spectrometer system, which is something that we're looking at continuously while we're roving in order to be able to look at the neutron count changes as an indication of where there could be water ice and where we should ultimately drill. In the green text, you see various features of the rover, including an explicit steer mobility system, very different than what you're used to seeing with a 6-wheel rocker bogie of traditional Mars rovers. The way we move and where we are in a polar region very much drives the design in order to accomplish our mission. Solar rays on the sides, which of course is because the sun doesn't get very high off the horizon when you're in a polar region. So you need to point to the sun, which would put it at nearly vertical angles along the sides of the rover. And then of course the radiators up on top, because nothing but the blackness of space up above. Then lots of situational awareness. Cameras all over the place, as you can imagine. performing basically two primary functions: navigation, of course, stereo imaging and so forth, all the way around, up on the mast, up on the top, but also hazard awareness, right? Cameras that are down located near the wheels. It's sometimes hard to see what's happening underneath you when you're using your nav cams to look out ahead. And so we have cameras down below as well. Quick overview of Viper in relation to other notable roving robotic missions. The top row there are familiar Mars rovers, and the bottom row are lunar vehicles. You can see how Viper compares. If we had more time, I would spend more time on some of the very interesting differences between Viper and those. Quick hits on a couple of them. It's a completely solar electric powered mission. You'll notice that plutonium and polonium are used quite extensively on the missions. There's reasons that we're not doing that. And then also we're a relatively fast rover. Relatively, maybe not in comparison to even a human walking, but in comparison to the rovers, we're pretty quick in being able to move around. This is being a fact. And then in a polar region, the lighting conditions, and that includes the shadows, are moving quite quickly. So the rover has to be able to move quite quickly too, to stay ahead of very dynamic. Now I'm going to move into some of the progress that we're making here in our development. This is a quick image of some of the lighting testing we've been doing at Ames, representing soil conditions, cratering, positive and negative relief conditions, solar lighting conditions, and helping the drivers understand what they might see through the lens of Viper's nav cams, but also understanding how to optimize some of the algorithms and stereo viz algorithms. This is a messy little picture. It's actually a clip from a video of a dust box test that we're doing of our rover release mechanism. And that's the rover release from the lander itself. We're going on a astrobotic lander through the CLIP vehicle, contracting, of course, lunar delivery means. And so this test here was just making sure that the rover release mechanism operated after what could be a very dirty landing. We're not quite sure, but we're taking a pretty aggressive stance on this through this test. We're also doing assembly pathfinder work. This is taking place at Johnson, and we've just completely refurbished a clean room out there. And this is some of the early practice work that we're doing. And you see in the aluminum there, just for this purpose of assembly pathfinder, this of course is not flight or even EDU hardware. We've built the lower frame, the belly pan, and some of the chassis parts for the rover. The red boxes, and there's blue boxes as well, are 3D prints of key components, and the team is already practicing assembling the rover. This is not the finished design, but it's getting the team used to operating in this environment, procedures writing, handling various pieces of equipment. For example, the image you're seeing now is of M Solo, a 3D print of M Solo. And just the whole activity of behaving with flight hardware and some of the peculiarities of how you have to insert, install, support humans holding, have hands here, but don't put hands there. So we're really getting quite serious very early in the flow on how we're going to build this to reduce risk later. This is a earlier RP-based, resource prospector-based rover that we've been using for extensive testing. This comes from a video clip as well, showing all the degree of freedom that the Viper rover has, quite a bit of articulation, which leads to both nominal and some off-nominal gates of movement. We haven't been down in these polar regions. We haven't been down in a PSR. And based on data from LCROSS, LRO, and other missions, it could be a very curious and challenging environment down there. We know it's going to be cold, but the exact nature of the soil, whether cemented and quite hard or downy and fluffy, is going to require us to have flexibility and capabilities out of our rover. So we're trying to design that in. We're also doing testing out at NASA Glenn at their slope facility. The top left corner there, you see a grill in the horizontal bed. That's the sink tank. We've spent a fair number of time down there. and have forced ourselves to sink and then have pulled ourselves back out, which is quite remarkable for the history of the sink tank and bodes well going forward. This incline, 25-degree incline that you see the rover test bed on right now, of course, is beyond the requirements performance of the rover. We're intentionally trying to get it to slip as we're moving up this angle, up this slope. And what it's doing is helping us understand and calibrate our pose estimates and our slip prediction algorithms. There's a number of flight software activities that we're doing here in order to be able to operate the mission with as high a confidence as possible, while we're also calibrating with an outer loop using stereo visualization optic flow techniques. So really quite impressive. And we're testing it very early to make sure we understand the limitations and to tune things up. And here we have the rover going down a mock-up of the Astrobotic Griffin lander. They actually shipped a mock-up out to NASA Johnson, where the rover is being built. And we were doing testing, going down their first iteration of rampways, as they call it. And we even, as you can see by the plywood blocks that are there, trying to cause some anomalies, right? We have a rampway that lands on a rock and twists the entire exit means. And so we've been doing testing with this as well, both with rigid suspension, meaning we're not doing active suspension. We just look like a rigid 4-bar system. And then also with a tuned suspension. So we're just really trying to get as smart as we can with the capabilities of the rover, both the highly capable and the more primitive, so that we have a very good familiarity when we actually find ourselves on the mission. Just thought I'd give a nod to COVID. The pandemic, of course, forced us to do a whole bunch from home. And so we've been teleworking like many of the rest of you. This is a driving simulation taking place at one of our training coordinators' office at home. And you can see on the left screen there, on that laptop is the driving tool, the commanding tool. On the right laptop, on the right side, you can see the situational awareness mapping and so forth of where we are driving, the locale. And in the center, you can see the nav cam images that are part of a very high fidelity simulation that we've got together. And then under the desk, you can see some feet warmers down. Final Viper mission status, we are on track to a late 2023 mission start, November, December. We're working through those service plans and scenarios now. Both our schedule and costs are tracking to plan, I'm pleased to say. We are holding multiple meetings with Astrobotic. As you can imagine, the level of integration and discussion that's required is incredible. We're working interfaces, loads, and requirements. The coupled loads analysis with SpaceX, the selected launch vehicle that we're going to be using, Falcon Heavy, are all being talked about and actively worked now. We're building design confidence through analog testing. You've now seen some still images of just that. This is just the very beginning of the physical interface testing with Astrobotic. Much more to come. We've delivered an entire wheel system up to them, up to their location in Pittsburgh, so that they could do testing there while we're simultaneously doing testing within NASA. We're also conjuring what we're calling last-ditch locomotion means should Viper get stuck. I say that acknowledging we haven't gotten stuck yet, but we're not reliant on that. So we're looking at different, unconventional, but within the capabilities of the rover, ways that we could find ourselves getting out of a stuck situation. So that's both fun and important, trying to understand the best trades there. And then finally, as a lead-in to Tony's talk, much site analysis and traverse testing trades are going on. And they're optimizing against the capabilities and constraints of the rover. As you heard, our CDR is coming up in October, which means the rover is done being designed at that point, and now you have to work with what you have, the rover that you ended up with. And so this is all part of that site analysis work, and the landing site selection will be revealed at the Viper CDR. And that's everything.
Great. Well, thank you so much, Dan. And we are all, again, so excited to have Viper, to be looking forward to Viper and all that it's going to reveal, and it's really going to be enabling for a sustainable future on the moon through identification of resources. So just fantastic.